Okay, so just speaking to Mr. Patek, and there's a couple of about 4 spec points which we haven't covered properly. We're looking through related to transition metals. This is due because the lesson's organized in a way that generally these were taught, transition lessons were taught before, hence these were covered in other topics. So let's go through this first one here. So on my screen you can see this was, says the redox potential for a transition metal ion changing from a higher to a lower oxidation state is influenced by pH and by the ligand. So at first this sounds rather complex, it's really not that complex. So let's have a look. So here is a transition metal ion. This is manganese plus 7. That's going to manganese plus 2. And you can see it's got a redox potential of plus 1.51 volts. Okay, and this is done in acidic conditions. If this was done in alkali conditions, so say this was no H plus here, let's say this was all OH minus, this number would be completely different. So it's just that understanding that this number here, plus 151, is if it's done in acidic conditions. If it was done in alkali conditions, it would be different. Do you need to know if it's more positive, more negative? No, just be aware that it will be a different reaction, so therefore it would be a different redox potential. Okay, so it also says that the redox potential for a transition metal ion changing from higher to lower oxidation state is influenced by the ligand. So here's an example here. So you can see this here might have a redox potential, so an E naught of, I don't know what it quite is, I think it's plus 0.43. Okay, so this ligand here, we can see that this is aqueous, so it's surrounded by 6 water molecules, so it's hexa-aqua copper 2 plus. And the spec point is simply saying if that wasn't hexa-aqua, say it was a different ligand, say it was copper chloride, well, this number would be different. Again, it's sort of obvious because it's like, well, this is a completely different reaction. It's a different ligand. Is a completely different reaction, so of course the redox potential will be different, but that's all that spec point means. Okay, another little spec point I think I didn't touch on properly. We did touch on maybe when we talked about catalytic converters. So it says the use of a support medium to maximize the surface area of a heterogeneous catalyzer and minimize the cost. So basically, say you've got a catalytic converter mainly made of palladium or platinum, okay, both very expensive metals. So making the whole thing solidly out of it is very expensive. Also, because the catalyst works by the chemicals adsorbing onto the surface, the inner part of it doesn't need to be pure platinum. So what you can do is you can create a support structure made out of something cheap and strong and then coat the catalyst on it, and that way it minimizes the cost. So that's all that means. Generally, we'd use a honeycomb structure because that has a large surface area, something strong, something cheap, coated in, say, the platinum. And this would be the same for any heterogeneous catalyst in an induction. Okay, so another spec point. This one we would have covered in thermodynamics, but at the end of thermodynamics, but we haven't done. So this one goes, bidentate and multidentate ligands replace monodentate ligands from complexes. This is called the, I was mispronounced this one, chelate effect. Students should be able to explain the chelate effect in terms of the balance between entropy and enthalpy changes in these reactions. So what does that mean? Okay, so here we have hexa-aqua chromium 3 plus reacting with diamino ethane. You can see it's going from 4 particles on the left and 7 particles on the right. So energetically, in terms of enthalpy, this reaction has a delta H close to 0. So if you think about delta G, that's also going to be close to 0. But if you think about the entropy, we're going from 4 particles to 7 particles. So actually the entropy has increased. Same thing for hexa-aqua chromium 3 plus with EDTA. We're now going from 2 particles to 7 particles, so entropy has increased. So, which of these reactions will be most favorable? where were we? Yeah, so the bottom one's going to be more favourable because the entropy the entropy change is becoming more positive. 2 particles to 7 is more chaotic than 4 particles to 7. Okay, so both of these have small delta H's in these substitution reactions, but they have big increases in entropy. So the products are more thermodynamically more stable than the reactants. This is known as the chelate effect. Okay, so the chelate effect is basically the situation where we have multidentate ligands replacing monodentate ligands. Even though the delta H is relatively, the reaction is relatively small, the entropy change is relatively large, making these reactions favorable. Okay, so you can prove this using the Gibbs free energy equation. Okay, so what's it saying? So complex ions with polydentate ligands are called chelates, and chelate complexes are favored over complexes with monodentate ligands. It's a chelate effect. Okay. Oops. So what is the chelate effect? The increase in number of particles causes a significant, as we just said, increase in entropy. Okay. So that's it for that spec point, and that's it for everything. Just try these questions now. So try this one up here, pause the video. Mark scheme's coming in a sec. And there we go, mark scheme. And then pause the video. Okay. Oh yeah, so what is the use? Why is EDTA, why is it useful? We're just going back here for a second. So if you swallow some metal, now generally a lot of these metals, transition metals, are very bad for you inside you. But EDTA is great because what it does is it will take the metal and it will form a complex with it. Now EDTA, I think is poisonous, but it's insoluble because it's a very large molecule, so it can't be absorbed into through your bloodstream, through your stomach even. So if you've had heavy metal poisoning, they actually give you EDTA, and the following reaction will occur, the one I can see right here, creating the complex with EDTA, and then you can get rid of that the normal way without getting poisoned by the metal. Okay. And that is it.